Welcome to this video on revision worksheet 16. So revision worksheet 16 was focused on geometry, and the question was the 2012 paper 1 section A question 6 paper. Now it's important to note that this was during the pilot phase of Project Maths, and during this time they did give an option within the question 6, the geometry question. So if you go back through the older papers, you'll notice that it would have a 6A or 6B. This is no longer the case. You just get your question. There is absolutely no choice on the paper. We will go through both parts. What we tended to see when there was a choice was there was maybe a more practical proving construction theorem question, and then there was a more problem solving, so figuring out how can I prove something using the theorems, and that proof or the show or the verify, whatever it was, and in this case we're going to see a proof. It can be quite difficult, but I always say remember there was a choice. Now that's not saying you couldn't get something like that, but do bear in mind that when these questions were asked there was a choice. So let's get to it. So question 6A, so this was the part A. So given the points B and C below, construct, without using a protractor or a set square, a point A such that A, B, C is equal to 60 degrees. Now, obviously on the computer I'm going to find it very difficult to do any kind of construction, so I have just layered in things. So if you want to see any of the constructions in more detail, there is a lot of fantastic videos up on YouTube already if you want to just put in that construction, or you can get step-by-step instructions on open reference as well, but I would suggest videos if you're struggling. So let's look at the logic of this. So they've given us a length BC. Now, without using a protractor, so we obviously can't measure 60 degrees. So what they're asking us to do there is figure out a way to draw 60 degrees without having any idea about sizes of angles. Now, the only thing that we know with regard to 60 degrees is that all equilateral triangles will have angles of 60 degrees in them, because a triangle must have 180 degrees. So if the three sides are the same, equilateral, then the three angles will also be the same, and that means 180 divided by 3, 60 degrees. So what we would do is, you can see it here now, we would construct the point A such that it is the same length between A and B as it is between B and C, and it is the same length between A and C as it is between B and C. How we would do that is you would put the compass point on B, you would open the compass to C, and you would draw an arc. Without changing the size of that compass, you would then put the point at C and draw an arc from B until it meets the first arc. That point there will be A. Drawing a line from B to A creates the angle that we want, ABC. And if we were to draw a line from A to C, that would create the equilateral triangle that contains 60, 60, 60. You don't need to complete the triangle because all they wanted was that angle ABC. So part 2 then says, hence construct on the same diagram above and using a compass and a straight edge only, an angle of 15 degrees. Now, there was 2 ways to do this. I think the most straightforward would be the idea of bisecting the angle and then bisecting again. So if we bisect a 60-degree angle using our bisecting of an angle construction, we will get 2 30-degree angles. If we then go along and bisect that 30-degree angle, we're going to get our 15-degree angle. So it should look something like this. The dotted line shows the first bisecting of an angle, and the second straight line lower down, that shows us our 15 degrees. It's important to clearly label, so clearly show your 15 degrees on the diagram. Another way that you could have done it, and I haven't got it worked here, but I will talk you through it, is that you could have used the idea that we have a 60-degree angle. You could have then worked with a 90-degree angle and split that in half, 45, and then use your 30. It's a little bit more complicated, it's a little bit longer. The method here is probably the most straightforward, but with geometry especially, there isn't ever just one method, so don't feel if you did it another way that you're wrong. Always double check to see, is your method valid, because it often, if you've been able to get to the same end point using good logic, it will be. So part B of this then said, in the diagram, L1, L2, L3 and L4 are parallel lines that make intercepts of equal length on the transversal K. Now that's actually one of your theorems that you need to know, but they've given that to us anyway. So we know that these lengths are the same. So I'm going to just go through and show the lengths that they basically told us are the same. So they've said this length equals this length equals this length. So FG, FG is parallel to K. So I'm just working through it. As they tell me something, I'm going to work through. So this line here, FG, is parallel to K. Okay, oh, sorry now. It's not really easy to draw on this, but we'll go with it. So they're parallel lines. The same logic applies to these lines. I'll just put in my little arrows here so we can clearly see it. Oh. And they said HG is parallel to ED. So this line here, I'll have it going down, is parallel to ED, and I'm just going to go over that in green. So what I often find with questions like this, they give a lot of information and they give a diagram, and it's always a good idea to work through the information that they give us, and if there's any information that they give you in the paragraph that is not on the diagram, that you put it on. So it's a really good practice to get into as you're going through a question, working through it, seeing is there anything here in this paragraph that's not given on the diagram. Don't assume that everything on the diagram is just that's it, that's all your information, because often they can throw in maybe one or two other little pieces. Sometimes they don't, but it's always good to double check. Another tip is color coding, or color coordinating. So you can see here, it's really clear to see what they've told me, and there's no assumption or no having to go back and check, oh, did they say this or did they say that. I can clearly see my HG there is parallel to ED because they're both in green. So then they want us to prove that the triangle CDE, so hopefully we can see that one down here, and the triangles FGH are congruent. Now, to prove congruency, I would always recommend the same method. So start with writing the triangles up the top. So CDE, and then over here FGH. We want to show congruency. Okay, so we want to show they're congruent. Congruent is three lines like this. What we will do is underneath this, we'll put everything got to do with triangle CDE. Underneath FGH, we'll put everything got to do with triangle FGH. That makes sure that you don't repeat anything, because sometimes I see students showing me something equal one way and then showing it just written the wrong way, written the opposite way. So they haven't really proven two things. So before we get into actually proving it's congruent, let's talk about congruent for a second. So you have a few different ways to prove it. So the first is side, side, side. The next is side, angle, side. Then we have angle, side, angle. And then we have right angle, hypotenuse, and another side. Now, I'm going to look and say, well, look, we do not have right angles here at all. So we're probably not going to be dealing with RHS. Now, what can we work with? Well, now we have either SSS, SAS, ASA, or SSS, SAS, or ASA. So there are three possible ways that we're going to be able to prove that this is congruent. Now, realistically, we're probably going to bring an angle into play. Just remember that proving that the three angles are equal does not necessarily prove that they are congruent. It proves that they are similar. And similar means they are the same shape but not necessarily the same size. So that is important to remember. So let's work first of all with FGH. So because of the way that this is drawn, I know this line here is parallel to this line. That was given. I know that this here, and I know I'm going over the colour I have, but bear with me, is parallel to this line. Okay, so what we have here, and what I'll do is I'll put in a few more letters to help us. So what we have, I'll call this A, and I'm going to call this B. So we're going to say F to A is parallel to GB. That was given to us. And FG is parallel to AB, and that was also given. Therefore, FABG is a parallelogram. Okay, so what does that mean for us? Well, therefore, the length of FG equals the length of AB. Okay, because it's opposite sides in a parallelogram. Parallelogram. Now, by that logic, so since AB equals BC equals CD, which was given, we can say that FG equals CD. Okay, so that gives us our first thing. So here we have CD in this triangle equals FG here. Now what I'm going to do is I'm going to put this as 1, and I'm going to label all this working as working 1. So this means I can quite easily link back to it if I need to. So they can clearly see how I worked through that logic to get that CD was equal to FG. So I have a side. So I know I was going to have to figure out one side at least, because side, 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 side angle, side angle, side angle, they all have a side in it. Now I need to figure out, well, another side or another angle, something. So let's work through. Now I'm going to use some dots to help. So this angle here, and we see that there, okay. And I'm going to work with red, so I'll say this one here. Okay, so I've hit a dot, and I'm going to put a blue dot in here. So there my, oh, they didn't stick. So there my angles. Now I'm going to work through and say, well, this one is equal because they are vertically opposite. It is also equal to this one here because it is corresponding. It is equal to this one here as well because this angle here was equal to this one because they are vertically opposite. This is also equal to this angle here, and it is equal to this angle here. So working through that, okay, and I'm just going to put in some notes. Okay, vertically opposite angles. This one was corresponding. This one is a vertically opposite angle. This one here is alternate. and this one here corresponding. So now I have an angle. I have that the angle DCE is equal to the angle GFH. I'm going to write a note on diagram. So that's worked through there. Okay. So now I have one angle. I have one side. So I have two options. Because of the way I've worked so far, I can either figure that the green angle in my triangle ECD and get that equal to this corresponding angle above in FGH, or I'll need to figure out that the length of EC is equal to the length of HF. If I work anything else out, I won't technically have side angle side or angle side angle, and I'd have to work again, and that's okay too. So what we're going to do to work with that green is I'm actually going to extend this line here. Apologies, that didn't. I'm just going to rub this out just for 1 second to clear it. So I'm just going to extend my line, which is currently H. Oh, it's not very straight. So from H to G, I'm just going to try continue that line. Sorry, now it's working a bit difficult on this. So effectively like this. So this is still parallel. So we now have HG extended. Now it's not extended to C. It's coming out some other point. However, what it does allow us to do, and again, I'm going to just rub out some of the bits here for just 1 second. Okay. So I'm going to extend this back again. And we basically create this angle here, and they are equal because they are corresponding. Okay, so that's my corresponding angle. And this angle here must also be equal to this angle here. And the reason they are equal is, again, corresponding. Now, my diagram is quite messy, but hopefully we can see that. So what we have here is the angle CDE equals the angle FGH, again on the diagram. So what we have proven, and again, I'm going to just take everything off this diagram for just clarity to see. So we'll get rid of all these bits. Okay. Clear the diagram. So what we've proven now is CD here equals FG here. We've also proven that this angle here, DCE, is equal to GFH. And we've also proven CDE and FGH. So clearly you can see, hopefully at this point, so we will say therefore triangle CDE. Now bear with me, for the method I'm going to use here I'm going to need perpendicular lines, but obviously I find that very difficult to draw when I'm using the computer. So first thing I'm going to do is I'm going to identify the fact that AB is actually a tangent to the circle. So if I drop a line here, it's going to be perpendicular. Similarly, if I do that here, AC is also a tangent, which means that here, ignoring that little line for a second, I have two right-angled triangles, I have two right angles, one at Q and one at P. These two dotted lines, what I've created is a quadrilateral, the quadrilateral OQAP. So what I can say is, because angle OQA, I'm just going to keep this written down as we go, that's also equal to angle OPA, and that's equal to 90 degrees, since AC and AB are tangents. Okay, so and the radius is perpendicular to the tangent. Okay, so by that logic, we have the quadrilateral APOQ, and it's not just any type of quadrilateral because the opposite angles add up to 90 degrees, it's a cyclic quadrilateral. And that's important. Cyclic quadrilaterals are going to be really, really important the whole way through. So what we can say then is, if I go, basically, if you can imagine it, and again, it's quite difficult to draw, but there's a circle that goes through all of these points. Okay, so that's a circle, and all these points are on the circle. So what we can say there then is O to Q to P is the same as O, sorry now, I need to move to another colour. So O to Q to P is the same size as O to A to P. So this angle here is the same as this angle here because they're standing on the same arc. So let's write that down. Angle OQP is equal to angle OAP, angle standing on the same arc. And we know that OAP is actually half of the full angle here. So it's actually half of that full angle here. So that's half of the angle P to A to Q. So that full angle there. And the reason we know that is because, I'm going to end up with so many colors, apologies. We have two triangles here. And this is kind of where we were working with the proof we did in class. We have two right angle triangles and they share that side. They're both right angles. So we were saying that they were congruent, and the reason they were congruent was RHS, right angle, the hypotenuse then which they share, and one other side. So this side equals this side because they're both radius. So because they're congruent, if I'm talking about this little piece here, that little angle here, which was angle OAP, it's half of the full angle because it's matched by this angle here because the two triangles are congruent, so therefore it must be half. So by using that same logic, so sorry, I'm just going to put this in OQP. So by using that kind of same logic, I'm just going to use the word similarly, because if you can prove it one way, you don't actually have to prove it a second way. So what we can say then is by saying, well, angle OQR, so O to Q to R. So we're dealing kind of with this side of the, sorry, I shouldn't really circle it, but we're dealing with that side of the triangle and the circle. So we know that OQR then is equal to half of QBR. It's exact same logic. So apologies, now just run out of space. So adding that, so angle OQP plus angle OQR will equal to a half of PAQ plus a half of angle QBR. And cleaning that up, so if you go to your diagram, O to Q to R and O to Q to P added together, sorry, so that's kind of the first line, so added together, that actually gives us angle PQR. And pulling that half out to the front leaves us with angle, now we have what's called PAQ, but that is absolutely fine to write as CAB, because that's just using the bigger triangle and the vertices of that bigger triangle, and that's what they want in the actual question. CBA, so that's QED, so done.